Hello, everyone. My name is Frank Sosa, and thank you for watching my presentation today. In this presentation, I will be addressing two key topics in sports biomechanics. First, we'll explore the concept of drag force in swimming and how different factors influence it. Then, we'll shift focus to analyze the biomechanical reasons behind athletes' collapse during the final stages of an Ironman marathon. Let's begin with our first topic understanding drag in swimming. So, what is drag force? To start, let's define drag. Drag is a resistive force that acts opposite to the direction of motion of a body moving through a fluid like water or air. In swimming, it's the primary external force resisting forward motion. Because swimmers are fully immersed in the water, they must constantly combat this resistance. Reducing drag is critical for energy efficiency and competitive performance. Three types of drag in swimming. There are three primary types of drags that swimmers face. Form drag or pressure drag arise from the swimmer's shape and how much frontal surface area is exposed to the water. Larger surface areas increase resistance. Wave drag occurs near the surface where a swimmer creates waves. The higher the swimmer's speed, the greater the wave resistance. Frictional drag is caused by the contact between the water and the swimmer's skin or swimsuit. The smoother the surface, the less resistance is encountered. Understanding how each type operates helps swimmers and coaches find ways to minimize them. So let's take a moment to break down these key biomechanical terms. Frontal surface area. This is the portion of the body that faces forward in the direction of movement. Smaller frontal area decreases form drag. Laminar versus turbulent flow. Laminar flow is smooth and orderly, while turbulent flow is chaotic. Turbulent flow increases frictional resistance. Wave interference. This describes how energy is transferred from the swimmer to the water, often increasing drag when nearer the surface. So, from a kinetic standpoint, drag can be analyzed with the following equation, where drag, where FD is the drag force, CD is the drag coefficient, lowercase p is the density of water, A is the frontal surface area, and V is the velocity. This equation shows that drag increases with the square velocity, meaning if a swimmer doubles their speed, the drag increases 4 times. This exponential relationship highlights the importance of streamlining. So now what influences drag in swimming? There are several factors. Bottom positioning, horizontal alignment reduces form drag by minimizing frontal area. Swimsuit technology, advanced swimsuits reduce both form and frictional drag. These were restricted post 2010 due to performance enhancement concerns. Velocity, higher speeds lead to significant higher drag. Technique, proper stroke mechanics and streamlined movements reduce turbulence and resistance. Morphology, long limbs and lean bodies naturally reduce drag. Each of these elements is something athletes and coaches can focus on in training and preparation. Empirical evidence supports these concepts that were mentioned before. Toussaint in 2002 showed that passive towing experiments confirmed streamlined positioning significantly reduced drag. Marino in 2009 used computational fluid dynamics to show that the body position and suit material affect drag. These research provide biomechanical justification for coaching strategies focused on drag reduction. To conclude the first question about drag force, minimizing drag is vital for swimming performance. Through the kinetic analysis and biomechanical understanding, we can see how body positioning, surface characteristics, and velocity interacts with water to influence resistance. Optimizing these factors can enhance both efficiency and speed in swimmers. So now let's move on to our second question. What causes athletes to collapse in the final portion of an Ironman marathon? These collapses are dramatic but can be explained through a biomechanical lens. We'll look at the kinetic breakdown, neuromuscular fatigue, energy depletion, and postural control failure. From a kinetic perspective, a collapsing athlete often loses the ability to generate adequate ground reaction force, or GRF, needed to stay upright. The equation is here. F, ground force reaction, equals mass times acceleration. As acceleration drops, muscle force output weakens. The body can no longer oppose gravity, leading to collapse. This especially affects the lower limbs extensors like the quadriceps and glutes, which are key to supporting body weight during stance and locomotion. Next, let's consider neuromuscular fatigue. Central fatigue disrupts the brain's ability to send signals to muscles. Peripheral fatigue limits the muscle's ability to respond to signals. During an Ironman, both types are likely present. Athletes experience diminished joint torque, especially at the hip and knee. Co-contraction of antagonist muscles also increase, which wastes energy and destabilizes movement. Energy depletion is another factor. Muscle glycogen and glucose stores are exhausted. ATP availability drops, impairing muscular contractions. Central nervous system coordination is impaired, as seen in the central governing theory proposed by Noakes in 2012. Additionally, dehydration and electrolyte loss interfere with nerve conduction and muscle excitability. This leads to cramping, loss of control, and contributes directly to collapse. Loss of postural control and proprioception. Maintaining posture during gait relies on neuromuscular feedback. Proprioceptive input from muscular and joint decreases, vestibular and visual balances systems degrade. This results in irregular foot strikes, increased medial lateral sway, loss of dynamic stability. These symptoms are evident in dramatic Ironman finishes like Julie's Moss, where athletes lose control of their legs and fall repeatedly. Research backs this breakdown. Millets in 2011 showed that ultra endurance race causes both central and peripheral fatigue, particularly affecting knee extensor torque. Saunders in 2005 found stride mechanics are impaired with fatigue, increasing risk of collapse. Hosworth in 2001 noted that aerobic efficiency and neuromuscular coordination both degrade under extreme stresses, which all backs up my previous slide. In summary, collapsing at the end of an Ironman marathon results from a biomechanical system failure. Inadequate force generation, neuromuscular fatigue, depleted energy, and impaired postural control of all converge under extreme endurance conditions. Understanding these mechanics can help athletes and coach better prepare, potentially preventing injury and improving recovery. Here are the pre-reviewed primary sources used throughout this presentation. These studies form the evidence base for understanding drag in swimming and the collapse in Ironman endurance athletes. Thank you for your attention and thank you for your time for this semester. Let me know if you have any questions. Thank you so much.